This video covers section 8.6 from the textbook, which deals with equations involving radicals. Now, anytime you're trying to solve an equation that involves a radical, we need to follow the following steps. And this is just kind of a loose framework to follow. Sometimes you might not need to use all of these steps, but essentially the best way to do this is to try to get the radicals on one side of the equation and everything else on the other side. Now, it's possible that you might have more than one radical. If you just simply have two radicals, then you just want to set them equal so that you can get rid of things. But if you have two radicals and another number or another expression, for instance, you usually want to get the radicals on the one side and everything else on the other side. So this is usually the rule that you want to follow. The second step is you're going to raise both sides of the equation to whatever power will eliminate that radical. So if it's a square root, you would square both sides. If it's a cube root, cube both sides. If it's a fourth root, raise both sides to the fourth power. Once you've simplified everything after this step, then you need to see if there's any radicals left, which is possible if you started off with two or more radicals in the equation to begin with. If so, repeat steps 1 and 2. Once you've eliminated all of the radicals, then you solve the equation with the typical rules of algebra, adding and subtracting from both sides, multiplying and dividing by coefficients, and taking roots again, possibly if you have powers of exponents, and factoring sometimes to solve for roots as well. So you're just going to use all of those rules that we've had previously from algebra. This fifth step is something that's new, and it is that we need to check for what are called extraneous solutions. Now, an extraneous solution is one in which that the process of actually solving the equation, so an extraneous solution is a value that arises due to the solution process but that does not make the original equation true. And we'll see what this means as we go through and solve some of these equations. So you want to check to make sure that the values you got actually make the equation true. And if not, then you throw those out and just keep the ones that work. So let's try our first example. We've got a square root of x minus 4 is equal to 7. In this case, we've got the square root on one side, the 7, the non-square root, on the other side. I don't want to see anybody trying to distribute the square root over plus and minus. We already talked about how you cannot distribute roots or exponents over plus and minus. So in this case, we keep everything as it is, and our first step in solving this is to square both sides to get rid of the radicals. So this would be step 3. So when we square the square root, we are left with x minus 4, and when we square 7, we are left with 49. To continue using our rules of algebra, we add 4 to both sides to solve for x, and we are left with x is equal to 53. Now we want to check to make sure that we do not have an extraneous solution. If you plug 53 in, we get the square root of 53 minus 4, and we always want to make sure that that radical goes over everything that's underneath it. So we get the square root of 53 minus 4. 53 minus 4 is 49. Square root of 49 is 7, which was what our original equation was. So we are good there. Sometimes we need to do a little bit of arithmetic or algebra before we simplify or take the roots. In this case, if you have a number outside the radical, you can still go through and square both sides, but you have to remember to square the 3 to get 9. Most people, however, choose to instead just divide by our coefficient like we would in algebra. And essentially we're still doing step 1 here, which is to get everything with the radical on one side and everything that's not under a radical on the other side. So the 3 divided by 3 would be gone. We'd be left with the square root of 2x minus 5. And the 15 divided by 3 would leave us with a 5. So now we would do step 2, which is to square both sides because we want to get rid of that radical. And then we'd be left with 2x minus 5. And on the right-hand side, we'd be left with 25. Again, using our rules of algebra, we're going to add 5 to both sides. And we're left with 2x is equal to 30. Last step, divide by 2 to get rid of that coefficient. And we are left with x is equal to 15. Again, we want to make sure that we check that this is correct and is not an extraneous root. If you were to plug this in, 3 times the square root of 2 times 15 minus 5. Well, this would be 3 times the square root of 2 times 15 is 30 minus 5. And that would be the square root of 25. So you would get 3 times 5, which is 15, which was what you started off with. So 15 actually ends up being the answer for this one. Now, I want you to pause the video. I know this one is a little bit different in that it's a cubic, but all we're going to have to do is take the cube root of both sides, follow example number 2, very similar, and go through and try to solve this one, and then resume the video to see if you have the correct answer. So in this case, you should have gotten that x was equal to 63, and if you go through and check to make sure it works, it does work out, so we're good. Our answer is x equals 63. We've got a few more examples here. In this case, we start off with just not a simple radical equals a number. We have to do a little bit of algebra again. So we need to make sure that everything under the radical is on one side, and that everything that's not under the radical is on the other side. So in this case, we are going to add the 4, and we end up with the square root of x plus 1 is going to be equal to 11 minus x when we add that 7 and 4. Now we have the radical on one side and everything else on the other, so we can use that step where we square everything, step 2. We are then left with x plus 1, and I want to make sure that everybody is clear that when we square 11 minus x, that we need to really think of this as being 11 minus x times 11 minus x. And by now you should have that kind of memorized down how you simplify that. But if not, you can go through and FOIL and simplify. Really make sure to practice that so you can get faster at it, because it will keep coming up in this math class and future math classes. So we end up with 11 squared, which is 121, minus 2 times 11 would be 22x, and then plus an x squared. So as far as solving algebraically, we would move our x and our 1 to the other side. We would be left with 0 is equal to, and I'm just going to write this in descending order, x squared minus 23x and plus 120. So, like I said, sometimes we need to go through and factor to actually find our solutions. We're going to end up with 2 solutions in this case, which we really want to check to make sure that nothing is extraneous. So, in this case, if we factor, we have to think of factors that multiply to be 120 and add to be negative 23. Now, take a second to think about this. So when you simplify this, when you factor this, you should have found x minus 15 and x minus 8 to be your factors. This is still equal to 0. So in this case, x is positive 15 or 8. Again, we want to check both of these to make sure that they are not extraneous roots. So if we check 15, again, we have to go back to the original equation when we haven't manipulated anything. We're going to take the square root of 15 plus 1, and then the whole thing minus 4, and we want to check, so I'm going to put a question mark over there because we're not sure if this is equal to 7 minus 15. So the square root of 15 plus 1 is 16 minus 4. Simplifying the other side, we get 7 minus 15 would be negative 8. Square root of 16 is 4 minus 4. This does not equal negative 8. So 15 is actually an extraneous root. It does not solve the equation. Now if we want to check 8, one of these has to work. We plug that in, we would get the square root of 8 plus 1, and then we would subtract 4, and we want to see if that is equal to 7 minus 8. So if we simplify again, 8 plus 1 is 9, minus 4, then we get 7 minus 8 would be negative 1. The square root of 9 is 3, minus 4 does end up being negative 1, so this works. We have one answer, and it is 8 in this case. So this was a case where we had an extraneous root. Try a few more examples here. In this case, we have 2 radicals, but it's not too bad because there's nothing else involved. It's just simply 2 radicals. And since we have the 2 radicals, we can just go to step 2, which is squaring both sides. And when we square the left side, we get rid of the square root, so we are left with 4x squared plus 2x plus 9. If we square the right side, we are left with 3x squared minus 2x plus 5. So that one wasn't too bad. All we need to do is move everything over, combine like terms. So I'm going to move the 3x squared over. I'm going to add the 2x, and I'm going to subtract the 5 to get everything. We want to set this equal to 0 so that we can factor. So we would move all of this over to the other side. And when we do, 4x squared minus 3x squared is going to leave us with an x squared. 2x plus 2x is going to give us a 4x, and 9 minus 5 is going to give us a plus 4. All of this is equal to 0. So now when we factor, we are left with x plus 2 quantity squared, which only gives us one answer. It's a repeated root. And it is that x equals negative 2. We want to check this. We only have to check on one at once because it's a repeated root. We would take the square root of 4 times negative 2 squared plus 2 times negative 2 plus 9 is equal to, we want to check this, so question mark, 3 times negative 2 squared minus 2 times negative 2 plus 5. So when we simplify here, we end up with 4 times 4, which is 16. Then we get a minus 4 and a plus 9. If we kind of just keep going down this side, we get 16 minus 4 is 12. 12 plus 9 is 21. On the right-hand side, we end up with a square root. We get 4 times 3 is 12. We get a positive 4, and we get a positive 5. So we want to see if this is equal. 12 plus 4 plus 5 is also 21. So this ends up working out. X equals negative 2 is our solution. We have a few more examples, a few more types to work through. In example 6, we've got a 4th root equal to a square root. So what we need to do is we need to take the root that is the highest power, which would be to the 4th power. And when we do that, we get rid of the x squared plus x. We get rid of the 4th root on this side, but we have to remember what this really means. This means x plus 1 to the 1/2, and then we are raising it to the 4th power. So if we multiply those exponents together, we get 1/2 times 4, which would be 2. So this really ends up being x plus 1 squared, because we have essentially 4 square roots, which is going to leave you with x plus 1 squared. So again, remember those laws of exponents. I want you guys to pause the video now, go through and finish solving this, and then check for extraneous roots. So when you worked all of this out, you should have gotten that x was equal to -1. Again, be careful when you're squaring out any kind of polynomial that you make sure that you write it out that many times, and then you FOIL or distribute. Do not distribute exponents over sums and differences. You should have gotten that x was -1, and when you go through and check that, it does indeed come out that you get the 4th root of 0 is equal to the square root of 0, and both are equal to 0. So it does work out in this case. This next example, we again have 2 square roots, but in this case we have this 3 as well to deal with. There are different ways that you can go about doing this. Personally, I prefer to keep both radicals on the same side. Some people like to put one radical on one side, one radical on the other side. It's really up to you. If you do, the one thing that we have to be very careful with here is that we're going to square to get rid of it. But we're going to have to essentially multiply these radicals together. Again, think about this as being the square root of x plus 7 plus the square root of x plus 4 times the square root of x plus 7 plus the square root of x plus 4. And then this is going to be equal to 9 in this case. So if we were to multiply this out, the square root of x plus 7 times the square root of x plus 7, those are the same thing. So we just get x plus 7. And I'm going to put it in parentheses just so we remember that that's what it was. It was from that term. Now for our outer pieces, or if we want to just think about the fact that this is FOILed, we would have 2, and we're going to have x plus square root of x plus 7 times the square root of x plus 4. And then the last, when we square the x plus 4 times x plus 4, we're going to be left with an x plus 4, still equal to 9. And now in this case, we can move the non-radical pieces over to the other side. So we would subtract x, subtract 7, subtract x, subtract 4. So over here we would be subtracting 2x, and we would be subtracting 11. So in this case, we have 2 times the square root of x plus 7 times the square root of x plus 4 is equal to negative 2x minus 2. We add that 9 in there. Again, we have to go through the same process, so this is one where we have to repeat the process because we still have a square root involved. We could divide here by 2, which would probably be a good idea to get rid of that coefficient. When we divide by 2, we are then just left with the square root of x plus 7 times the square root of x plus 4 is equal to negative x minus 1, because each one of those would be divided by 2. And now we would square both sides again. And the nice thing here is that since these are both square roots, we can distribute because they are multiplied together here. So we have x plus 7 times x plus 4. And then if we square the other side, we end up with an x squared. We would end up with a plus 2x in the middle, and we would end up with a plus 1 here. So now we need to keep going here. We're not done yet. When you multiply out x plus 7, x plus 4, you get x squared plus 11x plus 28. And still on the other side, we have x squared plus 2x plus 1. Now, again, we want to get everything to one side, set it equal to 0. It doesn't matter which way. Since the x squareds are going to subtract out, I'm going to move everything over here so we have a positive x. So I'm going to subtract x squared, 2x, and 1. And so then we are left with a 9x plus 27. And if we subtract that 27 over, left with 9x equals negative 27. Divide both sides by 9. And we are left with x equals negative 3. Now, again, we need to make sure to check to make sure this answer works. So when we check, we have the square root of negative 3 plus 7 plus the square root of negative 3 plus 4. And we want to see, does that equal 3? So we end up with the square root of 4 plus the square root of 1, which is going to end up being 2 plus 1, which is 3. So we're good on that case. X equals negative 3 is our answer. These last two examples now deal with what happens if we don't necessarily have numbers. It's possible that sometimes we need to solve equations just in general for a different variable and they involve a square root. So that's what these last two examples are. If we want to solve this for c, c is under the radical, so we need to get rid of the radical, get everything else out of there. So for me, the first step would be to divide by this 2 pi coefficient. So now we have t divided by 2 pi, just a fraction, is equal to the square root of r2c times r1 plus r2. And before we get too carried away here, I just want to point out that this would be an electric circuit. Example, R1 and R2 are resistances across a wire. They're not squared. This is not a squared exponent. This is a 2, labeling it as a second resistance and a first resistance. And C is a capacitance. So in this case, we want to still get rid of the square root. So we're going to square both sides here. We need to remember that when we square a fraction or anything involving multiplication and division, that we distribute to everything. So this is t squared. 2 squared would be 4 and pi squared. And then this is equal to r2c over r1 plus r2. So now we just have to deal with the algebra. We need to get rid of the denominator. So we're going to multiply by the entire denominator to get rid of it. And we are going to put it in parentheses. Remember, I said parentheses are very important because it means that we are multiplying the entire quantity, not just part of it. If you do not put those parentheses there, then you are only multiplying R2 by this fraction here and not the entire quantity, which is what you should be doing. So those are going to simplify to be 1, and we're going to be left with R1 plus R2 times t squared over 4 pi squared is equal to R2c. The last step that we need to do then is divide by R2. So we're going to divide that entire thing there by R2. And in this case, we're going to be left with R1 plus R2 in parentheses, very important, don't forget it, times the quantity t squared over 4 pi squared, all divided by R2. So I know that looks very messy, and we're not going to go through and check that one because it would be a little bit too involved. But this would be the same equation, only solved for capacitance instead. So I want you guys to try example 9. Pause the video now, see if you can work example 9. So for this one, if you went through, this is just talking about velocity. In this case, G would be gravitational force and H would be height. And V, we call this V naught, would be initial velocity. V sub 0 is usually called V naught. If you go through again, repeat all the steps that we've done so far, you should have ended up with H being V squared minus V naught squared. So initial velocity squared divided by negative 2G. This concludes the video for 8.6. Go online, complete your homework for this section, and then move on to the final video of Chapter 8, which is 8.7.